So the next thing that I am going to talk about is the eigenvalues of the system. So as I said earlier, that whenever we do a measurement on a system, or whenever, let us say, we do a measurement on any property of the system, for example momentum, the system will basically collapse to one of the allowed values of momentum, and these allowed values of momentum are known as the eigenvalues of the momentum operator. Or let us say if I do a measurement on the energy of the particles of a system, the system would basically collapse to one of the allowed values of energy of the system, and these allowed values of energy of the system are called the eigenvalues of the energy operator. Okay, so the first class might be a bit difficult to understand, but then I promise that it would become clearer and clearer when we move deeper into the course. Okay, so allowed values of a property of the system are known as eigenvalues of that property operator. For example, if we do a measurement of energy, then the allowed values of energy are known as the eigenvalues of the energy operator. Okay, so now a question might naturally come that why is it that a system would only have allowed values of energy or allowed values of momentum? Does or can it not assume any value of momentum? So the answer is of course no. A quantum system can't have or can only have specific values of properties or parameters, specific allowed values actually. Okay, now the second question is, can it happen? Okay, another point I would like to mention is that it is because of the specific allowed values the system is known as quantum. Okay, quantum, the term quantum basically comes from quantization, which means that you specify certain allowed values at given gaps in the system. Okay, or certain specific allowed values of the system. Okay, now the second question to naturally ask is that is it only in quantum systems that these specific allowed values exist? Because as far as we know that a classical system can have any value. For example, a classical system can have any value of momentum, or a classical system can have any value of energy. Okay, is it only a property of the quantum system that this specific allowed values exist? And the answer is that no. Even classical systems can have specific allowed values, or a classical system can have specific values if they are subject to boundary conditions. Most of the classical particles that we see in day-to-day life are not subject to boundary condition. For example, if I throw a ball, this ball will just move with some velocity v, and gradually due to friction this velocity would come down and it would eventually stop. There is no boundary condition here. Okay, so there is no boundary condition restricting this system. Okay, or let us say that if we throw a ball up in the air, then it would just move continuously. There is no boundary condition. Okay, but suppose we do have a boundary condition, and suppose a classical object behaves as a wave. For example, if we tie two ends of the string, so we have fixed two ends of the string with a pivot. A string is a kind of classical object, and there is this string over here. We have fixed this two end, and then we try to vibrate this thing. Okay, we pluck somewhere in the middle and we try to vibrate this thing. Can this thing have any value of k, where k is basically related to the momentum of the wave? So let us say that we have I try to vibrate this string, and the wave that develops on vibration is of the form, let us say, a sine kx. Okay, can this string assume any value of this k? Of course not, because this string is actually fixed at this point and at this point. So only those values of k are allowed for which the wave becomes 0 at this point and this point, because these 2 points cannot move up and down. These 2 points are basically fixed. So it cannot assume a continuous or any value of k, but it can only assume those values of k for which the vibration at this point and this point is exactly 0. And which is to say that if the length of this string is basically L here, then if this is x equal to 0 and this point is x equal to L, then we must have psi 0 equals to 0 and psi phi L equal to 0, because these 2 points cannot move at all, so these 2 points should not vibrate. Okay, so this function, this thing is already satisfied for this a sine kx, and for this condition to be 0, or for this condition to be satisfied, so we should have a sine kl to be 0, so which basically means kl should be equal to n pi. So k should be equal to n pi by l. So note that we have basically, where n of course is an integer and n is not equal to 0. So note that we have basically, by giving boundary conditions, so here the boundary conditions are that this string cannot vibrate at this end and this end. Okay, so we have fixed these two ends of the string, and by restricting these boundary conditions, we get a definite set of values of k which are allowed in the system, and these values of k are known as the eigenvalue of k in the system. Okay, so the specific values of k, the specific allowed values of k in the system are the eigenvalues of k vector in the system. Okay, so by giving specific boundary conditions, by telling that this string is not allowed to move at this point and this point, I am basically restricting the system to certain allowed values of k. So k cannot take the value of 3 pi by 2 to L. Okay, it can only take the value pi by L, 2 pi by L, 3 pi by L, etc. So this quantization or quantized values or specific set of allowed values, in other words the eigenvalues of a system, exist only in Now let us actually go into the mathematics of the course slowly. We'll not go into too much mathematics, but the minimal amount that is required to understand quantum transport. So we'll start with Schrodinger's equation. Schrodinger was actually the pioneer of non-relativistic quantum mechanics. So Schrodinger's equation basically governs the time and space evolution of non-relativistic quantum particles. We'll not discuss into the detail of where the Schrodinger's equations comes from or what is the basis of derivation of the Schrodinger's equation, but you can actually take it for granted, this equation, because this equation is so fundamental and so specific that you can actually trust this equation with your eyes closed basically. Okay, and it has been used for the last like 70-80 years, so it's basically that much fundamental, and you don't really need to know into the derivation of this equation, so you just have to know the equation itself. So this equation is I h bar del t of gamma equals to minus h square by 2m del 2 gamma del x2 plus v gamma. So here gamma is basically the wave function, and because we are actually studying electronic transport here, we would be considering this gamma to be the wave function of an electron. Okay, because electron is what is relevant to electronics. Okay, and we would be studying electronic transport, so we would be considering uh, the wave function of electrons only. Okay, now in the classical world we have functions for different properties. For example, if we want to find out what the kinetic energy is, the kinetic energy is basically a function of momentum, which is basically p square by 2m, or it can also be written as a function of the velocity, which is basically half mv square. Okay, so in the classical world, to convert one property from the other, or to find out one property from the other, we basically have functions. Okay, in the quantum world, we basically have operators instead of these functions. Okay, for example, if we want to find out also the momentum is a function of velocity, so it is mass times velocity, so again we have a function. So in the quantum world we have operators basically. Okay, so this operator minus h square by 2m del 2 del x2, this is basically the kinetic energy operator. Okay, so this operator, when acts on a wave function, gives you the kinetic energy of the system. Okay, this is the potential actually. So this is basically the kinetic energy here. This V is basically the potential energy. It can be an operator, it can be a function of space and time, or in the very simple case it can be just a number. Okay, in this course we would assume V to be a function of space, not a function of the wave function, but a function of space itself. Okay, because for example, if we have a heterostructure, we have the potential as a function of space, or if we have the p-n junction, the bands bend as we go from p side to n side, so the potential is basically a function of the space here. Okay, so as far as electronics is concerned, V is generally a constant number, or it is a function of space basically. Okay, so So this is basically the potential energy times the wave function. So the total combination is basically the sum of the potential energy operator plus the kinetic energy operator. Okay. So when we have the potential plus the kinetic energy, that gives me the total energy. So this operator I h bar del t, this is known as the total energy operator. This is known as the total energy operator. Okay. Now we have to solve this equation, and we'll start with a very simple case. So let us consider this equation I h bar del gamma del t equal to minus h square by 2m del 2 gamma del x2 plus v gamma. Now to solve this equation, we are solving the case of a free electron. So case of free electron. So again, free electron, just as I stated, means an electron which does not obey any boundary condition. It is completely free. Okay, it does not have any condition at its boundaries. Okay, so we are first solving the case of a free electron, and in this case what I will do is so gamma is basically a function of space and time because it is a wave function. So just as we can write a wave in the form of a sine kx minus omega t, so it is a function of space and time, and also you can also understand from this differential equation that gamma must be a function of time because we have this del gamma del t here, and gamma must also be a function of space because we have this del 2 gamma del x2 here. So gamma is basically a function of space and time. So we'll do a separation of variables here and write gamma as psi x times phi t. Okay, and we'll just plug this form in this equation over here. Okay, so when we plug this form, this equation basically becomes I h bar psi x del phi t del t is equal to minus h bar square by 2m phi t del 2 psi x del x2 plus v times phi t psi x. Now we divide by this quantity phi t psi x, and we get I h bar 1 by phi t del phi t del t equal to minus h square by 2m 1 by psi x del 2 psi x del x2 plus v. Now note that this part is basically a function of t. This part is basically a function of x. Okay, so when we have a function of x and a function of t, so this part is actually a function of t because this phi t is a function of t only and not a function of x. So this is a function of t. This part is also a function of t because phi t is a function of t only. So this part is only a function of t and not a function of x. The right side similarly, this psi x is a function of x and not a function of t, and so this del 2 psi x del x2, this one is also a function of x and not a function of t. So the left hand side is a function of t, the right hand side is a function of x, and this would happen for all values of t and all values of x. So these two cannot be a function of either t or x, but these two must be equal to a constant, and we call this constant as E. Okay, so now from this equation you can basically find that phi t basically has the solution a e to the power minus I e by h bar t. Okay, and psi x basically subject to the condition that v is equal to 0, psi x basically has the solution b e to the power minus I k x, where k is equal to 2m e minus v divided by h bar root. Okay, so this is basically your assignment for the next day, to show these solutions for a free particle wave. So show that the solution to the electron wave function for a completely free electron are given by the above equations, and hence argue that k and E can take any values. So just as I said that for a completely free electron, k and E are not restricted to a specific set of values, but they can assume any values, and from there we again conclude that the specific allowed values of particles in quantum mechanics, or the specific allowed values of quantum particles for a given property arise only from boundary conditions. Okay, so this is your assignment for the next day, and you have to submit the assignment, and you would be graded on this assignment. Okay, so we'll do up to here today. Thank you everyone.